Hi everyone, my name is Lohann, and today I will talk about cross-chain interoperability. I am blockchain engineer at Analogy One, and here our goal is creating the tools that will allow developers to build truly decentralized cross-chain applications. So we will start out with an overview of bit security and the fundamental difference between various cross-chain protocols. Then finally, we'll dive into the Timechain protocol and the big picture architecture. There, I will present you to the game theory mechanisms that will implement the protocol and how the Timechain allow blockchains to trustless exchange messages. So first of all, it's important to highlight that there are a lot of insecure bits out there. All of them claim to be secure and decentralized, even when they clearly don't. Usually those breeds will work fine until the point where the value required by them exceeds their weak security assumptions. That's when hackers will come in and exploit the loopholes in the protocol. As a result, we found ourselves in this reality where just 2 years of bridge thefts alone are now paired with 24 years of centralized exchange exploits. Even Vitalik Buterin, who itself helped building a lot of cross-chain protocols, is now skeptical about the cross-chain future, which is understandable. After all, the cross-chain future that we dreamed and the reality are very different. But with so many different solutions out there, what are the key differences between those breeds? Well, from the technical perspective, there are just 4 categories: centralized or multi-signatory schemes, such as Wormhole and Chainlink CCIP, and as the name implies, they work pretty much like Oracle. There's also light clients, which are the most secure bit solutions out there, but at the same time they are the less compatible ones. One example of light client solution is this no bridge protocol, which is composed of 2 light clients, one light client on Polkadot that reads Ethereum state, and one light client on Ethereum that reads Polkadot state. Moving forward to the next one, we have hashed time lock contracts, which is actually the first technique created that allowed 2 persons in different blockchains to trustless exchange assets. One solution that uses technology is the Decred decentralized exchange. HTLCs, different than light clients, are very simple and very compatible. Works, for example, to trustless exchange assets between Bitcoin and Litecoin. They, however, are also very limited. We only know how to exchange assets. We don't know how to use them for send arbitrary messages. And last, we also have collateralized based breeds. This solution is designed for asset portability, not for arbitrary messages. It works like a cross-chain version of MakerDAO protocol. It's used by the interlay bridge to allow anyone to mint wrapped Bitcoin on Polkadot by locking Bitcoins on the Bitcoin blockchain. So now let's talk about the specific properties that we are interested in those breeds. Soundness is the ability of the bridge to reject invalid messages. Liveness means that breeds must not have a single point of failure and must guarantee delivery or deliverability of messages. Auditability, we can see all past and present operations performed by a given bridge, so anyone can detect failures. Compatibility is about where I can use this bridge. Does that work between Bitcoin and Litecoin? Does that work between Ethereum and Polkadot? And finally, efficiency is how much cost for deliver a message. And what's the minimal delay to deliver that message? Does it cost $1? Does this cost $10? I should wait 10 minutes? I should wait 10 hours? And there are other very important properties as well, but I will not cover them on this presentation. So let's talk about light clients. Light clients is pretty much one piece of logic in one chain that can verify the consensus of another chain. As such, they are considered the most secure and trustless solution out there. So if they are the most secure solution and they are trustless, why is not everyone using light clients? Turns out that light clients have several limitations, and those limitations push back their adoption. First, they are complex. and requires a lot of engineering and research to build truly secure light clients. Second, they are chain specific. A light client that can read Ethereum mainnet state will not necessarily work for Moonbeam and A-Star, for example, even when all those chains are EVM compatible. Third, and the most critical point, is that it can only be implemented in very specific blockchains that supports a very specific set of cryptographic primitives, such as a specific hash function, a specific signature scheme, some zero-knowledge primitive. This drastically limits the range of blockchains that you can communicate with. And last, depending on the consensus protocol and cryptographic primitives, they can be really expensive to run on-chain. Turn them out into impractical solutions for some protocols like Solana, for example. So, while most research is being focused on how improve efficiency, like Polkadot Beefy consensus, not much work has been done on how to improve the compatibility. As a result, if your goal is connecting the highest number of blockchains possible, we see that the most bridge solutions are using centralized or multi-signatory schemes instead of light clients. So let's see how that mechanism works. This is Alice, and this is the trusted oracle, and we have here two blockchains, A-Star and Ethereum. On A-Star, we have a gateway contract managed by the trusted oracle. And on Ethereum, we have a ERC20 token that trusts on the trusted oracle. Alice wants to send a message for transfer some funds on Ethereum blockchain, but she have an account on A-Star. Alice first send a message to this oracle gateway contract, specifying the destination chain, the address, and the message data. The oracle listens to events from this contract and receives the Alice message. The oracle built a transaction with the Alice payload and signed that message. The Ethereum contract receives that message from the oracle and validates the signature. If it was the oracle who signed that, the ERC20 contract just assumed that it was valid. The ERC20 contract have no means to verify if that happened or not on A-Star network. He simply trusts the trusted oracle. It's easy to see why such bridge is not secure in a trustless environment. Nothing prevents this trusted oracle from forging a message and send that to the ERC20 contract. Even so, the majority of the bridge solutions out there are using this exactly same design, except that they do some minor changes by adding more trusted oracle and combining them into a multi-signature or a threshold signature scheme. And with this, they will claim that their bridge is secure and decentralized. But the point is, we already know what happens when we trust in such bridges. So there's no magic. We only know those two technologies for sending cross-chain messages, and both have their limitations. If your application just wants to communicate with a single blockchain and there is a light client bridge available there, then your choice is easy. But if you want to communicate with various different blockchains without compromising security, you don't have any good options available right now. We believe that other bridges using notarial schemes failed because they are inherently trusted and centralized. Most of them just assume that a given subset of oracles are online and honest. There's no accountability or punishment. If an oracle misbehaves by censoring messages or leaks its private key, the bridge users are the only losers in this game. Aware of those limitations, in the next section we will learn how the Timechain fixes the centralized notarial scheme. The first big difference is that anyone can be an oracle, including anonymous agents. We want to safely allow anyone to assume the role of oracle. As such, if an oracle has the opportunity to misbehave, he will do so, oracles are not running a charity. They are economically rational agents and will behave according to their own interests, ignoring how it can affect other users in the protocol. So to address that, the time chain uses game theory. The protocol guarantees that all oracles are accountable and their interests are aligned with the protocol main objective. We do so by using two types of incentives. First, oracles are not altruistic. They are just following the protocol because they are paid for doing so. Second, we also need some sort of insurance. So, oracles are required to perform a deposit in the time chain, and this deposit will be slashed if the time chain detects any misbehavior. We also have a special name for oracles that committed to the time chain protocol. We call them chronicles. So from now on, I will use the word chronicle to refer to individual oracles that committed to the time chain protocol. By the perspective of chronicle, those are the actions he can do. First, he must provide deposit D on the time chain. Now, he is committed to the protocol. And then the chronicle is left with two choices. Either the chronicle can perform a desired action, receive a payment for doing that, and later, when he decides to exit the protocol, he will be reimbursed. So now the chronicle have more money than what he started with. On the other hand, the chronicle can perform an undesired action, and by doing so, we will slash him and he will be kicked from the protocol. So we must assume that if a chronicle decides to take the undesired action, that's because he will actually make more money than what he would gain by following the protocol. So we can say that the chronicle decision is based on the incentives on both sides of this equation, where V is a private value that represents the utility or profit that a chronicle can make by not following the protocol, such as forging a message or being offline. If the left side of this condition is greater than the right side, we expect that the chronicle will go for the undesired action. Otherwise, if the payment on the right side of this equation is higher, we expect that the chronicle will perform the desired action. So those are the basic decisions. And for our bridge to be secure, this condition must hold for the entire lifetime of the protocol. The payoff for following the protocol must always be greater than the payoff for not following the protocol. To balance this equation for the desired behavior, we can take some actions. First, we can require more deposits and provide a better payment for the chronicle. And second, and more importantly, we must set an upper bound limit on the V value, which basically means limit the opportunities that a chronicle can profit from misbehavior. However, defining an optimal payment and deposit is not an easy task. Increasing the payment means increase the fees paid by users using the bridge. And the deposit, also known as collateral, must consider uncertainty factors, like currency fluctuations, bribbing, etc. As a result, we must encode those uncertainty factors in the deposit. But by requiring more deposits from chronicles, it creates an opportunity cost. We make the protocol less attractive for chronicles. Because why I would have my money locked in this protocol when I can make better use of it in another protocol? So we have this dilemma of opposing motivations. In one side, we have the chronicle who prefers lower deposits, because deposits are opportunity cost. In the other side, we have the user who prefer higher deposits, because this gives him more protection against chronicle misbehavior. So the question is, can we increase protection without increased deposits? One way you can do that is by requesting multiple chronicles to validate the same message. This gives us the next piece of the puzzle, Timechain shards. The problem we need to solve is how we combine the collateral of multiple chronicles in one message. Once we are using notary scheme, this is equivalent to ask how we can verify that multiple chronicles signed the same message. One solution would be verify all the signatures, but this does not scale. To keep the protocol secure, we need that each message to be backed by sufficient collateral. which can mean hundreds of chronicles. We also could use some interesting cryptographic primitives such as BLS signatures, but then it adds an extra constraint that all blockchains must support those cryptographic primitives, which reduce the range of blockchains that we can support. The most compatible and efficient solution is threshold signature schemes. It allows any subset of participants to generate a valid signature indistinguishable from one created without TSS. In the time chain, when we have a group of chronicles together in a threshold scheme, we call it a shard. To illustrate how shards are constructed, let's define two hypothetical values, C and M. C is the minimal collateral for the entire shard, while M is the minimal collateral for each chronicle of the shard. The size of the shard is based on the combined deposit of each members, which must be equal or greater than the minimal collateral C. All members have equal power to prevent some vulnerabilities. Then we use two formulas, one that defines the shard size based on its members' minimal deposits. Then the other formula defines the threshold and requires that 2/3 of all members are needed to create a valid signature. Once a shard is created, in this example, any subset of 4 chronicles can generate a valid signature. Also note that shards of different size can coexist. The M value can change from shard to shard, while the minimal backing collateral C is global. These mechanisms allow chronicles with different budgets to contribute to the bridge security, making the time chain truly decentralized. Also note that if more than 1/3 of all chronicles within the same shard are offline, it can completely halt the shard. To avoid that, the time chain requires that all chronicles must submit proofs that they are online to the time chain. Offline chronicles will be removed and punished, allowing new chronicles to join the shard. But there's also the situation where chronicles can be online but just censorship some specific messages. In such case, that will not be effective because any other shard can forward the message, and the malicious chronicles will just not receive the payment. There is another serious threat that 2/3 of chronicles within the same shard can forge and sign any arbitrary message. In such case, that will be very unlikely to be effective because many shards are chosen handling to verify messages signed by other shards. A single honest shard can reject the message, initiate a dispute where all chronicles must participate. Messages also cannot be executed directly in the destination chain. There is a smart contract enforcing a relative time lock of X blocks on every message, forcing the malicious chronicle to review the malicious message. The time chain also requires that all messages must be first approved by the time chain. If a shard assigns a message that was not approved by the time chain, it can be easily proved by anyone. The evil shard will be slashed, and the time chain will initiate a process for revoking the shard keys, also preventing that message from being executed.